Okay, great. Very good afternoon to all of you. I'm Afroz. I'm from Brunei. I work as a senior assistant professor, and my work is mainly related to hazards. So I think what I'm going to do today is to conclude what we have done so far. Is it not working? Yeah, sorry. I can get that mic also. That's fine. I mean the one which is in the hand because I move around.
Sound check. Can I check that?
Yeah, you can check what? Okay. Is the placement like should be here or is fine? Hello? Is it fine now? No.
Yeah, it's there.
Yeah, because some here and all.
Just keep it here, cause for the connection.
Where?
In the pocket.
There's no problem. Sorry. Okay, can you hear me now? Is this double? Okay, great. So what I'm going to do, I will more or less conclude what we have done so far here. As you can see, the title is Understanding the Transition of Hazards to Disasters. So the main focus is how the hazards are basically transiting into disasters. And the disaster, I mean, if you ask me, if you ask me, I would say that there should not be any Congress called a disaster management because we will not have disasters in the first place. And that is the mission, what I will be trying to understand. So for disaster management, there are three major things that we need to consider. One is that the scientific and engineering institutions, which we all are part of, and then we have the administration, and then we have public. I come from Kashmir, and I can tell you that the problem is the science is not translating into action. And I'll be talking here for the whole day, maybe from the next year. Next year, I'll be talking again about the management, but on ground, there will be absolutely no action. I've been writing newspaper articles for more than 10 years, and my brother is constructing a house in Kashmir, and he did not contact me asking me how I should build an earthquake resilient like a house. Now you can understand that is the problem. It's not like they don't have money, they have money, like he has money to do that. But I do not, sorry, see again, it's not working, right? Can you hear me? Okay, I can shout. That's fine, okay, that's fine, I can manage now. So as you can see, the problem is how the scientific thing is not really going into administration. Again, another problem is why are scientists and engineers not sitting in one place? I mean, I fail to understand this. Because see, I'm here for what? I'm here to basically do something so that I can save lives. If I can publish in Nature and not save lives, I'll not be happy for that. Because my main aim is to actually save people, save lives, save animals, you know, the plants and other types of life. So the problem is, okay, science is there. I mean, if you go back to scientific, the wisdom, is more or less 200 years we have spent in earthquake sciences. And they will tell you the same thing. Your building should be strong. Why are our buildings not strong? Am I adding anything new? No. I'm telling the same story. Maybe I'm adding new science to it. I'm understanding how faults work, how basically, how the faulting process works. But I'm not adding to that wisdom anything new. But on ground, it's not working. So therefore, there has to be a very strong connection with administration. If you do not make this connection, I can tell you I will be here for the next 10 years talking this, but there will be Hiroshima, there will be other disasters, there will be Kashmir in 2014, we had a huge flood there. There will be problems, the Pakistan earthquake where we lost 80,000, which can easily be managed. But we lost 80,000. Recently, we lost almost 2,000 people in a very small earthquake in Afghanistan. You know Afghanistan's condition. Like the small earthquake can create a huge problem. So as you can see, the problem is here that the administration is not taking the science into action. So, and then public is like, okay, public, what is public? We are scientists, we have nothing to do with the public. They should be here. I should have one section of people sitting next to us talking. I mean, all of these people should be here if we really want to address the problem, if we really want to solve it. If we really want to just like keep on adding titles and increasing our H index by publishing a lot of papers, that can work. but then we will not be really solving the problem, which is the main problem, is how managing the disasters. So as you can see, earthquakes, for example, in terms of the science, the challenge is not like in science we have a lot of challenges in terms of the earthquake science. As Professor Gupta has rightly said, there are basically seismic gaps. These probably are knowledge gaps. How do we know there are seismic gaps? We do not have really that strong evidence to say how far can you go. You can't really go that far in terms of the trenching. And so whatever information we have is limited. Therefore, there are huge challenges, and you are here to solve those challenges. We had seen 2005. You can ask still many people in a scientific community. They will say this earthquake was not expected. Why not? I mean, just tell me why not. Same thing with 2004. Any person who knows ABC of subduction system, they know that all subduction systems are capable of producing megathrust earthquakes, and they are related to tsunamis. So if we say that tsunami hazard is new thing, I will be surprised. Any student will be surprised. Why? Because, and then we have realized, then when we studied, then we see, oh, there was tsunami. So the problem is that we need something really bad to happen. I think it's probably the psyche of humans, and then we start acting. We're not really solving the problem. For example, you've seen most of the, if you read papers in terms of hazards and earthquake hazards in what do you call this, India-Eurasia subduction, this convergence, collision. Most of these papers are published on frontal fault. It becomes just like a fashion. Frontal fault is very active. Everybody goes there. The question is, do you understand the process? Do you understand why are not earthquakes in the interior areas? And when you have an interior earthquake, then you're saying, hey, this is a surprise. No, this is not a surprise. This is a surprise for people who do not understand how basically the collision system works. And if you ask anyone, like, they will understand, okay, just like, for example, the two cars are colliding, the front is going to get hit more, but other people on the back will also have some impact. They will have less impact, but they will have some impact. And that was the motivation that we looked into the interior of the collision zones, and we found a lot of evidences that there are actually active faults within the interior Himalayas also, right? Same thing as I said, the tsunamis. So there is a lot of science that you can basically work on and then do a great job. Here, you have seen, just a few days back, I think, we had an earthquake. Again, there's a huge debate on that. This is a new paper just published. Earthquakes are sometimes twins. Sometimes they can be triplets, but rarely they are quadruplets, right? So you can have 4 earthquakes. Normally they were saying, okay, here's a subduction zone. It is locking, it's locking. It's going to have big earthquake later. But that was the main consensus. But then you have small earthquakes happening in Afghanistan. Why do you have 4 earthquakes? Why not just 1? See, it's again challenging the main consensus that we had, that there will be a big earthquake and not the small earthquake that can release in different times. So they are now understanding how things work. I'll show you later some of the examples from field. They're not really from the active area, but it is actually an area very interesting because it depends on how faults interact, how the two faults interact, or if the fault is bending or not. Therefore, whatever we are understand, you cannot keep one number on a particular fault unless and until you really understand it. And I think that's really something that young people can understand. So faults connect us. I mean, this is a big motivation for me, because if you understand that how faults connect us, look at this beautiful fault. Some will say, no, it's not beautiful, it's causing earthquakes. For me, it's beautiful. Like, you got a subduction system here, and then it changes into the collision system. We are connected, right? All these like from South to Southeast Asia, if you really understand this whole system, what do you need to do? You need to collaborate, right? Don't keep the border so tight that I cannot do field work somewhere else, but I want to really learn. So there has to be like a very strong scientific community, particularly in Asia, in South and Southeast Asia, where we can come together and have restriction-free field work and everything to understand it. What hazards tell me? Hazards tell me that it connects people. It doesn't differentiate between lines, differentiate between what we have so-called the geographical lines. We actually follow tectonic lines. And as I said, it connects all of this. You can see these earthquakes. So whenever disaster happens, if it happens for example, in neighboring Pakistan, or it happens in Nepal, it can impact India also. It happens with us, it can impact other countries. So same thing we have seen here. Like you have seen this more or less impacted. So if you have a huge this disaster, it impacts more countries. So, oh, sorry. Now, this is like typically considered, as I said initially, what is called the in-sequence faulting is the people who are working in the collision zones. They're like, okay, you have a collision, then there will be a fault, it gets activated, and then the new fault comes in the front. That's like what is called the in-sequence. Now, sometimes what happens, this guy, the old one, gets activated. Now, don't ask why, right? It gets activated. It hasn't moved. No, I want to activate now. Because people were in it thought, okay, this is the model that everybody accepts. I want to accept this model. So therefore, what happened? Because of this model, everybody was concentrating here. They're not putting eye on the backside, right? And then if an earthquake happens at the backside, it can create trouble. So what I'm saying is that I really don't think that this model works. What I feel is, and when I was looking into the papers, there's a paper by Morley. He actually used a very good term. He used regressive. So he used a regressive term in terms of and I think that's a really nice term, because this is very aggressive. This is regressive. This is not like it's not going to activate. It will activate sometime. We don't know what, but we should not say that these are not active. So again, yeah, this is about the 2004, as you can see here. When they digged into this area, and they found these, you can see that highly variable recurrence of tsunamis in this 7,400 years of history. So what I was trying to point out was that subduction zones have a history of tsunami hazards. So therefore, we should basically, wherever we have subduction zone, we should keep in mind that we have to make sure there's a very strong tsunami warning system in that area, even if we do not have history of earthquakes. Now, this is really interesting. If you look at these earthquakes, this area looks really random, right? And here is more or less systematic earthquakes coming out from this. And that can easily tell you that there are two different, the collision is not symmetrical, it's asymmetrical. Here is more or less symmetrical, but here definitely not. So therefore, this seismicity and this tectonics is different compared to this one, even though they are same area. And again, as I said, this is something for young people to explore, but I can tell you that this is totally different than this one. There's no match. So we cannot match hazards of this with this one. The hazard will be different. And as you can see from seismicity, almost no seismicity here, then we have earthquakes recently there. So this was considered, okay, it's not really seismic. And what I want to, like from this image, which I created, look at these beautiful areas where you have normal faults. As most of you know, you have India colliding, you would expect thrusts. Most of the thrusts will be north, south, northwest, southeast will be the strike. But why are you creating normal faults? And also the thrusts. There are thrusts here which go basically northeast, southwest. I mean, how can you do that? What it tells you, these are young active faults. That clearly tells you that the way we are thinking about how it is happening here does not work, at least in this area. And remember, this is the area where you have the turning of this whole system of the faults, right? So therefore, the way we are thinking about this area is different here. Now, another important thing is that we have a lot of normal faults here. And they were talking about these lakes, and we have one paper on this where when we map more or less types of lakes, we found a very strong correlation with faulting. And you have the faults, for example, in this area. Most of these lakes are basically sitting in a pull-apart basin. And here, they are sitting mostly in rifts. You have a rift, and the lake is there, it's filled with water. So that is very important for particularly people who are working on lakes. That's why I was in that Congress. I was the only geologist there, but I deliberately went there. The reason was because if you ask any people who are working in lakes, they will have absolutely no understanding about geology. There's no link to geology. But as you can see, there's a strong link between geology and how the lake formation happens. Because remember, whole thing, whatever is here, is an outcome of interaction of India with Eurasia. So how can you basically take it out? This is the base. Your everything is happening here because of the interaction of the two. So if you are not using that information to tell stories about your lakes or whatever, it's not going to work. And that is a fact. And I can show you many examples like that. Therefore, I mean, you know, there should be a strong collaboration between people from different disciplines. Now, this is a map which we created. We're still working on it, so it is not final. But as you can see, that now why it is not final? I like this kind of maps. What it shows you, it actually shows you the rupture length, how big a rupture will be in that particular segment of the fault. Because remember that the faults are segments, and this segmentation is mostly based on where I found that there is a change in the strike of the fault. And I use this change in the strike, plus also we use the dip information from the earthquakes, and also where there are basically where we have information about subsurface structure, mainly from Nepal area. So we need seismic sections. Do you understand? If you really want to understand this, we need seismic sections throughout this area so that we know subsurface. Otherwise, all the models that we will make, I can tell you, they will not going to work. You can write it down now. Why? Because these faults, most of them are blind. And we don't have at the surface structure. We can see it. So they are actually coming from, let's say, 15 kilometers or more than 10 kilometers depth. We don't have that information. So how can I make a model of saying how big this rupture area will be if I do not have that information, right? And therefore, as I said, like those are things that you need to consider while making a model about the whole area and how big an earthquake can erupt in this area. Now, Kashmir is earthquakes, the tectonic storytellers, right? And so here, you can understand why is Kashmir there in the first place. This is something really beautiful basin, not like I am from there, but it is beautiful. Like you have seen this, it has a huge mountains surrounded by a nice basin. Look at the basin is parallel to the major fault, frontal fault. So it's not coincidence. It's not coincidence that it's like this. I would like, okay, Kashmir basin, can you be like this? Right, but it's not like that. It has like a length like this. It goes parallel to the northwest southeast section. And then, okay, fine, it is a pull apart basin, it's a piggyback basin. Then piggyback basins form like this. You got like a fault sitting on top. Okay, you got a basin here. But then who is stopping it from both sides? Like, how can you have the basin constrained between these two things? Because the fault is parallel. So this is something that still we do not have an answer to yet. And there is one person, it's called, the Burbank. He has worked a lot on this area. But I think, I asked the same question to him. He still doesn't have this answer. So we do not understand yet. But there is like, what I understand was that this basin was somewhere here, and then it has tilted to this position. That's what my understanding. But I feel that it is tilted, and that's why it was initially, a four-land basin somewhere here. And then it was tilted before this started rising, and the mountains rise later, and that's where its present position is. That's my conceptual model. Again, based on my crazy understanding, but we need more evidence to basically prove that. But again, as I said, that this is something really exciting and interesting basin to look at. Here, look at this Indus River. The river follows a fault. How can a river cut through the whole thing? Same thing goes here. Right? You got a river, and then suddenly it changed track. How? And it goes basically, follows a basin and then runs on the mountains from basin to mountain, right? So there is a very structural control on what we see here. Something we need to learn, right? So as I said, the out of sequence faulting, I think, is not really something that we should be basically writing. We should basically call them as regressive faults. And we can discuss more on this. Now, I highlighted some of the faults that are really alien, and one of those are this normal fault and these. So the lines that I'm putting, they are strikes. So remember that we are only expecting these strikes. The strikes are going like this, clearly telling you that there is extension happening here, and also telling you that there's compression. There's a structure which is basically going from here and then turns like this, and that's why we have thrusting there. So therefore, that structure has to be active, and it is active. As you can see, the normal faults there, so a reverse faults there. So therefore, if tomorrow there were an earthquake on this, it will not be a surprise. Okay, we expect those earthquakes to be there. Okay, great. So is there a link between active tectonics and flood hazard? There are many people who actually question me on this, like, how can you relate earthquakes with floods? As I said, that people are disconnected with these. I was like, no, there is a strong connection. topography is created. Okay, here, these are the mountains, right? You're rising the mountains, and when the mountains rise, the river starts forming. How can you form a river in the plain, right? So these rivers are forming here, and they're making big gorges because you are actually rising the mountains. So how are you saying that this is not connected with the river? How is it like that? There's no disconnect, there's a direct link. And as I said, this is a problem because most of the geology and geographers, we are not sitting together. It's very good, but most of them, they are not sitting together, just like we are not sitting with engineers. And that's why this whole disconnect is because of that. And again, if you really understand this, it actually tells you the same story, that you need to communicate with each other. You can't make disciplines just like for the sake of disciplines. You have to communicate, and then you can actually learn to understand more about hazards or whatever it is. So Earth structure makes us, the Earth is like that. It makes us basically colleagues. So here, what I've seen is that you have, if you have visited Kashmir, you will see it, that this area is, the subsided, and this is uplifted. This was basically a lake in the past. You can have the lake deposits there. That's a big story. Just to tell you that this story at least, that here we have an uplifted area, and this is subsided. So therefore, what happens when you uplift this? You basically have this area up. So therefore, there will be more carving of the rivers. So they will bring more sediments, and they will put those sediments somewhere here. And that, what is going to happen? Because it's a basin, so that there is going to build up sediments, and that is going to create more hazards, flood hazards, right? And if you look what happened during 2004 floods, yeah, that's 2014. This is paper I published in 2013. This is coming from 2014, and this is actually the tectonic geomorphic boundary that I marked from the paper, and now I mark it on the flood. You can see that it clearly marks that boundary, and flooding is not crossing that boundary. So my paper was in 2013, and this flood was in 2014. So as you can see that there's a clear link that this area is subsided topographically, and that's why this whole area is actually inundated, including Srinagar, and it accumulates water for quite some time. Almost, you can see the timing. See 35 days. 35 days, water. How much of the problem is happening to the local people, and they were disconnected, like the schools and everything. It's a huge trouble. And also the depth. So now, another important thing is the complex world of measuring displacements. For example, we have used GPS to measure the slip rates. We're also using the slip rates from satellite images, right? And what I want to highlight is that slip rates are going to change. And that's why from one paper to another, when you read slip rates, you're like, why are they different? They have to change. And the reason for that is because we can, okay, sure. I'll show you in a moment why. Because faults are basically not lines, they're zones, number one. If there's a big zone of fault here and small zone here, this area will have small displacements more, and this will have more displacement. So therefore, the slip rate from one segment of the fault to the another segment of the fault is going to change. And it is bound to change because from structural evidence, we have very strong evidence to prove that. So I will take you to that, the evidence to Borneo. Again, here, what I want to highlight is, look at this. This megathrust comes here and turns. So some of you who are interested in tectonics, go and work here, because this is fascinating. Like, how can you have a subduction system turning almost to 180 degree, and then you have huge basin formation. They're very young basins forming right here. I have some of the examples from Brunei, where we found really beautiful structures. Look at this. This is actually an area where we took this drone. So it's a drone image, and this is mainly sandstone and shale. So these guys are sandstone, as you can see. You can see the legend here, right? So somewhere there. And then you can see there is basically fault. It has a wider zone here. Just look at because the photograph was taken from from here. It's an aerial view. So it is wider, the zone is very wide, and it gets narrower as you go down here. You can easily see why, right? Here, what is happening here? It is dominated by shale. And what is happening here is dominated by sandstone. So what is going to be slip rate here? It's going to be more. It's the same fault. Displacing right now. Displacing more here, less here. Why? Because of because of what is here, what is it displacing. So this is something really interesting to understand that, so sandstone has porosity, right? It has more pores, so you can basically make a lot of big, what you call this, these zones of displacement. When you have a big zone of displacement, you basically have more room to relax, right? So that's why you actually have a lot of room, and here you have less, so that displacement is going to be more. And I think it's very interesting to find this kind of information in the Himalayan faults, the active faults. We can't do that. Why? You know that when you open seismic, trench, it's really difficult to basically map the trench because of this soft sediments. This one is, so in terms of active faults, if the active faults are going through very old rocks, it will be easy to see it. But for young, I think it's a bit difficult. And look at this beautiful structure. So here what has happened, fault comes here, turns. And when it turns, it actually makes what you call a compressional bend. And most of the deformation is concentrated here. So in other words, you take a sample here, no deformation. You take a sample here, highly deformed. You go a little bit out, not really much deformation. So you can see the deformation profile change. Just, okay, go from here. It's not much deformation here. There will be a lot of deformation here. Why? Because it's actually a compressional bend. So and now think about this in terms of the big, these areas, big faults, they can do the same thing. They can actually lock deformation mostly in one area. Okay, sorry, I'm running more or less there. So, okay, another challenge, I have 5 minutes, right? No? Oh, because there's no one, great. Okay, so the other challenges are that the morph in hazards into disasters. I am from Kashmir, as I said earlier. My brother did not listen to me, so nobody listens there. I don't know why, so that administration should check. We need some checkpoints on that. So again, this is an area which has been flooded. Here, look at this. This area is hugely flooded, was hugely flooded, but there is so much of, what do you call this, the urbanization going on. I can't check it, right? It is the administration job. Scientists can't do it. We don't have a say in this. Now, all the houses, this is a new house, right? It's going to crumble like a car of deck during an earthquake, unfortunately. Look at these beautiful houses. Beauty lies in safety, not in this. Just keep that in mind. So here, all the houses, they were much more better, and we had been discussing this in the morning also. So we come from what is called, this is called a regression. This is not called a progression. How is it progression? We go from safe to unsafe side. I mean, how is it development? Just tell me. And this is something that we need to think about. And now this is really interesting and very important. This was 1895. Unfortunately, the Srinagar should have been built on the present site. This is Walter Lawrence, the valley of Kashmir Valley. What I'm telling you right now was already there. Why people have not listened to them? I mean, just tell me, how are we going to change this world? If there's wisdom, there's everything. Well, I don't know how we don't want to change. I mean, this is really unfortunate. Okay, we must turn challenges into opportunities, okay, because you are the people who are going to make this happen. You have to make sure that hazards are not morphed into disasters. And we did this in the science outreach activity. You just do that. And this is something that I will stop here. That what you should be doing is this. So I actually, apart from science, right, apart from publications, which is normal thing, I also do this science outreach, local newspapers. You can write in any language, which is very good, but it's very important to interact with people and make some progress on that. Okay, thank you very much, and sorry for taking more time. If you have questions, I'm ready now.
I think we have had a lovely session, and it's indeed a